todavía no comparto. Bien. ¿Listo, Salvador? Y ya Salvador se perdió, vamos a ver. Ahora sí ya. Muy bien. Bueno, ya hay con paciencia porque se actualizó el programa y es un poco diferente ahora. Okay, so let's start now. Nice. Okay, right. So remember from last time, we saw vector bundles, and a particular type of vector bundles is the tangent bundle. In order to think of a vector bundle or a tangent bundle, you have your manifold M, and above each point on the manifold, you have a vector space. In the case of the tangent bundle, that vector space is the tangent plane, the tangent space at that point. And also we saw that when we have a vector bundle, we have a particular type of functions that go from the manifold to the total space. Those functions are called sections, and the whole idea is at every point you assign a vector that belongs to the vector space above that point, and those are the sections. And in that language, for the case of the tangent bundle, we have vector fields. So this is what we're going to study today, vector fields. And here is where we are going to use some notions of ordinary differential equations. And also, basically, this is like the first part where we are actually seeing applications. Everything that we have seen before is just to obtain manifolds, even by the definition, by the atlas, or submanifolds in a given manifold. We use the constant rank theorem and so on. So far we have viewed only manifolds. You have a good sense of that. And then for a manifold, we constructed smooth functions between manifolds. Later on, we defined a tangent plane. And with the tangent space, we managed to talk about differentials. And now we're going to see vector fields. So you are familiar with vector fields. This is something that you have seen. This is a vector field in R2. And for a manifold M, remember that this is our notation of the set of vector fields. We have something like this, right? Moreover, when we were studying this, yeah, this is the thing that I don't like is going nuts. So given a chart, we know how a vector field looks like. And moreover, we are always interested in smooth objects. In this case, a smooth vector field. And that means that the coefficient functions are smooth manifolds on that open set of the chart. Right? Now, also, if we fix a point, remember that we have what we call the derivation. At every point, we have a derivation. And moreover, when we plug in a function, what we get is another function. So this is something very important. That's the definition is here. This is very important because we can have a characterization of a smooth vector field. So a smooth vector field is smooth if and only if this function is also smooth. And so let's try to see this just to warm up with our concepts. So this is being smooth is something local. It is a concept that it is in a small neighborhood of a point. That's the concept of smoothness. The same that you know from calculus. So let's pick a chart. And again, we have this description of the vector field. Like this. This is something that we know very well. And this is the definition that we used before. It's smooth if all of these functions are smooth. That's the definition that we gave several weeks ago regarding smooth vector fields. Okay, then let's take some smooth function on M, and then at least on U, we have this. So this is only on U. Right, because the coordinate chart, the xi only makes sense on the open set U. Nice. And yeah, that's here at the bottom, I just wrote it down like the product of functions. The function A evaluated at a point, the differential evaluated, and all of that. Right, so with this, we have that the sum and product of a smooth function is smooth. So my hypothesis, this is smooth. F is infinity, so this function is also smooth, right? Hence, this function is smooth, okay? In a neighborhood, or at least in U. So we have to do that on every neighborhood. Pick a point, a chart, and you will have smoothness of this function. Y ya se fue Jesús. Salvador, si estás aquí, puedes conectar. No, ya vi que se salió otra vez. Ahora sí ya. ¿Todo bien?
Sí, ahora sí ya.
Ok. Y voy a ponerla mejor horizontal porque, digo, con esta nueva configuración todavía no me acostumbro. Muy bien. So, I have that X is a smooth vector field. I take a smooth function, and what I want to prove is that this is a smooth function. That's what I want to prove. So I will do that locally. So for every point, I take a neighborhood. Moreover, it has to be a chart, and I have to show that that function is smooth in that open set. Right, so we pick a chart. I have this, my hypothesis, X is a smooth vector field. So these functions are smooth. And now I pick any function, a smooth function f. Then my definition, I have this, right? That's the definition of a derivation acting on a function. But if you prefer to write down the coordinates, you have this. Remember, the aim is to show that this is a smooth function. And it happened that it is smooth on U. Because the A are smooth, the F are C infinity. Once that I apply the differential, I get a C infinity function. And so with that, we are done with this first part. Right? So with this, we finish the first direction. Now, when we were defining derivations and vector fields, this is where it is important to notice why it is C infinity is crucial here. Because if f is of order ck, this function will be of order 1 less. Because here, this will be k minus 1, not ck. So that's why it is useful to think of a vector field as a type of derivative. We lower the degree by 1. So that's what happens if instead of looking at C infinity functions, we consider functions of order k differentiable. So we have to be careful with that. And that one, it is useful to have C infinity functions. Everything works out very well, and we don't have to worry about the order. Now, let's look at the other way around. You have a vector field. That means at every point I have a vector of the tangent space, but I don't know if that vector field is smooth. We would like to show that it is smooth. The only thing that we know is that every time that I have a C infinity function, this is C infinity. That's what we know. Obviously, by this I mean C infinity on all of the manifold. I want to show that the vector field is smooth. Again, we will prove this locally. I take a chart. And remember that we have seen that the coordinate functions of a chart, compatible chart, are C infinity. Hence, also we know because X is a vector field, it looks like this. What we want to show is that these functions on U are C infinity. And that way we will be done. We know that X is a C infinity vector field. So we want to show that A1, A2, up to AN are C infinity functions. So here is some technical aspect. Because if you would like to see that this is, we want to show that A1 is C infinity. And then you might think, okay, so let's evaluate at the smooth function xi. You can do that. But however, know that the hypothesis, we need to evaluate the vector field on a global function. F has to be global. Right? So here F is like this. So every time that I have a smooth function on M, I get another smooth function on M, which is this one. So if I go into this and I apply xj, that will be a function of U, but we cannot use the hypothesis. So this is a technical detail, and this is what we have to do. Imagine that here I have M. I have U, and somewhere here is my function xj. So I need to extend aj to a C infinity function, a global C infinity function. So we are going, the way to do that is the following. I don't know if you have seen this in topology, but we need to consider a bump function. Oops, no. So, Salvador, have you seen a bump function?
I don't think so.
Okay. So that's what we need here. So first, let me tell you what it is. I will not give the proof. Okay. First, let me give it to you in terms of of topology. Usually, how it is as follows. You have two open sets. On X. X has to be, I think, a normal topological space. Remember that Hausdorff is, if you have 2 points, 2 distinct points, there are 2 neighborhoods about each point, and they don't intersect the 2 neighborhoods. Normal, you have 2 closed sets, you have 2 neighborhoods around them, and they don't intersect. So when you have something like this, you can do the following. You have a continuous function such that the following holds. This is X. V is my open set. Here I have U, another open set, smaller. So you have a continuous function that looks like this, real value continuous function. On U, the function equals 1, constant 1. On the complement of V is 0. But it has to be continuous, so something like this. Okay? Is this clear, Salvador?
Yes.
Okay, so here only topological space and continuous stuff. Now, this type of functions are very useful and have many applications. I'm going to express one, and that's actually what we're going to do. So what is an application of that is the following. So assume that you have U not an open set. and a continuous function. The whole idea is to extend G to a global function. So U is defined on an open set, but by some reason you require to have a global object. So you would like to extend it by a continuous function, and you will try that it equals U, it equals G on U, right? So then what you do is the following. This is your topological space. And this is U naught. I don't know if I need to make it smaller or bigger, so we will see in a second. So then consider a bigger open set that contains U naught. This is V. And then you have the bump function. So the whole idea is to take into account this new function, G times so first, so that's a global function. It must be continuous, and it also agrees with G. Well, the first one is obvious because F is 1, but the second one, it requires more effort to show that it is continuous. Okay? So this is an application of bump functions. In order, if you have a local object, how to make it into a global object. Here I only discussed the continuous case, but you also need to consider for this class the smooth case. The open sets is the same, but instead of having F continuous, we will require F to be smooth. And the application is the same. G, a smooth function, can be extended to all of the manifold by using a bump function. So, any questions here?
Uh, this U naught is smaller from the original U in which G is defined, right?
Right. So the U naught first come from hypothesis. I have an open set and a function defined there. So the open set is given. For instance, let's think of a metric spaces. So you are giving U naught open. The way that you come up with V, you can think of V as the at every point of U, fix an epsilon. And at every point of U, choose the ball or radius epsilon. The union of that is going to give you V, for example. It will be an open set containing U naught. So you need to have a bigger set. Now, to be honest, I don't remember if this is correct or the F that I take has to, if I need to have a smaller.
Because
Yeah,
this G is the one that is defined in the chart, right?
that will be the one in the chart. Yeah, no,
Yeah.
you know, this is incorrect. Let's do it like this, and then everything will be more obvious. You have this. I will take a U and a V different. So this is how continuity is going to work. This is U naught. Okay, I'm going to, U naught is going to play the role of V. I'm going to take another small set, U, and this is my function. So the global function that we have is the same, F times G. Now, in this case, you can see that it is continuous, right? Because G is continuous on U naught. Here, at that point, G is continuous, F is continuous. Here, here, here. But what happens here? Well, because it's already constant, it's going to be continuous. Okay? So, yeah, so this is more accurate. So this is identically G, not on the domain of G, but on a smaller set. And this one, you can choose. Okay? So I'm extending G, but it's not equal to G everywhere on U naught, only on a small set. So this is what, like for instance, if this is G, the graph of G, the extension doesn't look like that, it looks something like this. Here it agrees, only here. And then I don't know. But that's the extension of the function. Only here agrees with the function, not on all of the domain. Yeah, the first approach was incorrect because I don't think continuity can be guaranteed. Because I mean, just take it was obviously incorrect what I said before. If this is G, well, I don't know. I don't know if you can make it like this continuously. But at least this one is for me more obvious that it is continuous. Right, so bump functions, they are used basically like this. If you have something local, you can extend it. Because sometimes your objects require global things. So this is bump functions. Again, you can do this on the smooth sense category. And that's exactly what we have to do here. So let's start. I know that X is a vector field such that every time that I plug in a function, I get a smooth function. I would like to prove that X is a smooth vector field. So let's say I would like to show that it is smooth on a point P. I take a chart around P, call it U. The functions are smooth. And moreover, X looks like this. And then I would like to show that the functions A are smooth. And what I'm going to show that they are smooth first in a small neighborhood of P, maybe smaller than U, not in U, by extending by a bump function. Okay? And that's exactly what I was writing here. This is a smooth extension of the function xj. But again, maybe it agrees with the function xj in a smaller neighborhood. if I put P here, then here it agrees. But then again, and now with this global function, you can apply the vector field. And then the coordinate functions are going to be smooth. Okay, so this is the concept for bump functions. Salvador, any questions?
No, that's good.
Okay, now this is the thing that what I was telling you at the beginning. So far, manifolds, we have seen how to get manifolds, but we haven't seen nothing beyond in interesting aspects of them. This is the first thing that we will see, which goes into that direction that you can do on manifolds. So I have a manifold and a vector field. I'm going to define an integral curve. An integral curve, repeat, of the vector field x is going to be a smooth function from an open interval on the real line to the manifold. So far we know what smooth means here. That interval a comma b is going to have the zero, and that's where this comes. This is just a normalization aspect. The important aspect is this one. This is what we care about. I don't know if you have seen this before, Salvador?
The integral groups?
I'm sorry?
The integral groups? Or
Yes.
yeah,
So I don't know if in differential equations, if you see something like this.
and not really because we were more focused on the techniques and applications than
Okay. Right.
the more
Okay.
mathematical things.
Right. So we're going to see many examples on Euclidean space to get your hands on this. But basically, we are doing this. We start with a vector field and we have a smooth curve. So the way to think of this, the vector field infinitesimal stuff, and we're going to get something continuous, which is the curve. So this is what we're doing. We have a vector field on our manifold, and we are trying to find a curve such that every is tangent to the vector field. So there's a curve that at every point the derivative of the curve agrees with the vector field. This is what we're doing. And well, let's see a couple of examples and then we will see the theory. Maybe I want to start with this example here. So our manifold is just in plane. Our vector field, something very easy, is just flowing. It is a constant vector field that flows like that only. Constant. I wrote it there. Then I need a curve written here, C1, C2. I will put some initial condition. The point BQ, some fixed point. I don't know, maybe here. That's PQ. But this is the equation that needs to hold. So that's the equation of the definition of an integral curve. And this is, as we will see, it is a differential equation or a system of differential equations. So the left-hand side, so let's see if you have more room here. Remember the left-hand side here, it is just dx. And now the derivative should be, the derivative is exactly this. The vector field evaluated at this point, here it is. There's the definition. So I'm just rewriting the equations. Okay, and then I just put them together in brackets. I have two equations. C1 has to be the constant 1, C2, I mean the derivative of C1 has to be constant 1. The derivative of C2 has to be the constant 0. And I have to solve that system of ordinary differential equations. Oops. The first one is very easy to, you see, it has to be a constant, but remember that we have an initial condition. So we know what C2 is. Okay? That one is clear. Now, what about C1? Also, we have it here. That's what C1 is. Because we have this initial condition right here. Okay? Now, the domain of solution of this, I put it in red because that's going to be important later on. I mean, solving these equations, just by solving the equations, you know that solution holds for all t, the first one and the second one. Okay? That's just by looking at system of differential equations. Hence, we found the integral curve of the vector field. At 0, it equals p comma q, and if you take the derivative, it's going to be d dx, right? And let me put that here. Any questions?
I'm confused why we wrote the partial of x.
Okay, hold on. Here?
Yeah.
Okay. Yeah, with this. From here, let's see. That makes sense? Okay, now here. And that's exactly what I have here. Sorry for that, let me put it here. So this left-hand side, I put it here. This right-hand side is here. This answer your question, Salvador?
Yes, it is.
Are you sure? Because this is very important. So I'm avoiding this, but here you can put at c of t, this vector at this point, because this belongs to R2, or manifold. Okay? So,
It's the chain rule, right?
no.
Oh, then I got more confused.
Wait, let's see. For the right-hand side, this is a function from R to R2. So maybe it's the chain rule, I don't know what you mean by that. And then you want to take the derivative of this with respect to t. So sometimes you would write it like this. The partial with respect to t of this entry, comma, with respect to t of this. But already this is Not the notation that you might have used in calculus, but remember that this is a vector, right? So instead of that, you can also write first entry, second entry.
Yeah, that makes sense.
And when you see the notes, that's why I wrote down these two distinct notations. They mean the same, right? So applying the differential, this is in TP, sorry. Like this, right? By the definition of this differential.
Yeah, I wanted to think of C as just as a vector, but yeah, I forgot that it's just equivalent.
Okay, so this makes sense now?
Yes, it does.
And now as vectors, I have to match up each entry, the corresponding entries. And that's how we get this system of equations. That's clear?
Yes, thank you.
Okay, great. So we have that. So we have that system of ordinary differential equations. They are constant, but we have some initial condition, and we get this. So up to here, everything makes sense?
Yes.
Nice. Now, so remember that, let's say PQ, if this is PQ, the base point, then the image of C is just a horizontal line. At 0, it takes the value of E comma T. And in fact, you can see if you take the derivative, you will get the dx. So this is an integral curve. Now, this is something that I really want to stress. I'm going to change this example a tiny bit because I want to make an observation of this. So we arrive to these conclusions or to these two solutions based on our knowledge of solving a differential equation, an ordinary differential equation that holds for all t. Now, let me change the manifold a little bit. I'm going to remove the origin. And the vector field is going to be the same. The only difference is that we don't have that point. The origin is missing from my manifold. And again, the problem is the same. Find an integral curve for that vector field on that manifold. The only difference is when our base point is either here or here. We have to be careful there. For the other points, the same argument works. So I decided to take 1, 0, which is somewhere here. I just wrote what we had before, the solution. Is this, yes. P plus T, comma T, right? So that's what I'm doing. I'm not doing nothing different. But what I would like to stress is the domain of T, which is no longer R. The domain is this as opposed to all of the reals that we had before. And the reason is very simple. The domain of that function, you cannot increase it because otherwise it will hit the origin, and that's not part of the manifold. Okay? So, sorry, where are we? Here. That is, there are two aspects that come into play here. First is the solution of the ordinary differential equations. That will give you a domain for your parameter T. But the other thing, you have to look at the geometry of your manifold and see if that makes sense. And that's what happened here when we replace the manifold by this. So you have to be careful what is the domain here. Also, what is this? Also, so far we have only defined what is an integral curve. Later we will define a maximum integral curve. And that's where this type of aspects will come into play. Now, also something that you can also know from your previous knowledge, here you use this theorem from ordinary differential equations that if there's a solution and you have an initial point, the solution is unique. So this is going to be the unique integral curve that at time t equals 0 equals p comma t. So again, we have to be careful of what we mean by a unique integral curve. So that's something also that it is very useful. Okay, I'm going to give you a different example. I just want you to have this. This one we will have to work it out together. So now I try to have a non-trivial vector field as before. I have this. We have seen this vector field before. And I would like to find an integral curve. I haven't said about which point. So let's say that, well, in a second we will say that base point. Let me put it here. I want this to be 0, 1. That's going to be our initial condition. Okay? What I wrote here, Jesus, is just the definition of that vector field X. Let me go up so that you can see what's the definition of the vector field. Minus Y and X. And that's what we have here. Un momento. Okay, sorry about that. Now, Jesus, the first line is just the definition of the vector field. That makes sense?
Yes.
Okay, and now on the second line, I just have the derivative of the curve. So let's put all of this information together so that we will have the system of ordinary differential equations. So it is this, but with the condition that C1 at 0 equals 0 and C2 at 0 equals 1. So we have to solve that system of ordinary differential equations. Do you know the answer for that, Salvador?
I don't remember it.
Okay. So this is, let's see, C1. This is the general solution. we need to find the parameters A, B, A prime, and B prime. So, for instance, if you take the derivative of the first one, let's see that more or less agrees. You need to tell me what is this.
That should be, let's see, a times cosine of t minus b times sine of t.
Okay, so, and that has to be equal to minus C2, right? So, what is it?
So that should
B
be
minus A,
yep.
yeah. And let's check that. If you take the derivative of this, it's going to give you C1. Yes, they agree. So again, this is like a reminder. So we have the solution, but we have two parameters, A and B. But that's no problem because we have two initial conditions. Okay? And that's how we are going to get the values of A and B. For instance, C1 has to be equals to 0 and 0. That will give me what? From this one.
Mm, b0.
And from the second one,
That is minus 1.
pardon?
That a is minus 1.
Minus 1. Okay?
Yeah.
And so now you have your solution. So C1 equals minus, and C2 cosine. Okay?
Yep.
Uh, I don't know if this is right. The integral curve has to be a circle center at the origin that passes through the point. In this case, will be of radius 1. Yeah, sine,
Minus looks weird.
yeah, why is that? Sine has to be positive. Or maybe I draw something and the vector field is different. I don't know if that's the problem here. Let's see. Let's see if the vector field agrees with the picture. Maybe that's my mistake. No, that looks okay, right?
Yeah, it's fine.
Oh, right. No, it's right. The mistake that I made is here. Look, this is what is wrong. So let's keep this, but it's not this point, it's the one above. Okay? Yeah, so that's the mistake. The initial point or base point is this one. So there's no problem if the first entry is minus sign, has to be negative. Exactly. Yeah, so that's my mistake there. If you change the base point, you will get something different. Okay, so this is correct. And this is for all real numbers. You're going in circles more than once, and there you have it. Now, just to make this comment here, if you don't remember, the whole idea is to take the second derivative, then C double prime, double dot, it will be equal to minus C, 1. That's how you solve, that's how you arrive to this thing. If you take the second derivative, you will get the solution for this. Okay. Any questions?
No.
Right. So I'm going to end here. This is something very useful for beyond manifolds. Yeah, I don't like this new. So on the first example, the collection of all interval curves looks like this. In the second example, I forgot to mention this, but give me a second. Moreover, we have a direction. So all of the curves are oriented in some ways. And that's important because if I go on the other way, I don't get ddx, I will get minus ddx. So also the circles come with an orientation given by the vector field. So these things that we are doing with vector fields and interval curves our picture like this that maybe you have seen somewhere. When we put all of the integral curves together, we have like a flow. We will study flows later on. So far, we have only defined an integral curve, only one line. But we will put all of the lines together. And you can think as a fluid, how it moves, depending on the expression of the vector field, how it moves, okay? So just to finish, I forgot this observation, which is very important here. And with that, I would like to wrap things up. Okay, that's the equation of an integral curve. It is just in one line, but it is actually a system of differential equations. Now, the observation, and this is a question, assume that the vector field vanishes at one point. And the question is, what is the integral curve? From a point P.
Will it be like constant?
It's a constant, right? So the domain is all of the reals. And is that everything from a point? Okay. That's precisely the integral curve when the vector field vanishes at a point. This is just from calculus. The function has to be constant. Great. Okay, then, so we are done. So we will continue after the break. Any questions or comments?
No, I don't think so. ¿Tiene un minuto ahorita acabando de la grabación?